What NASA doesn't say about the edge of the universe, space, the final frontier, a realm so vast, so ancient, so thoroughly indifferent to our existence that even the most powerful telescopes humanity has ever constructed can only scratch the surface of what lies out there. We have mapped craters on Mars. We have tasted the chemistry of comets. We have photographed galaxies so distant that their light left before our planet had even formed. And yet, for all of this extraordinary progress, for all the press conferences and mission briefings, and carefully worded statements from the world's foremost space agencies, there is a conversation that rarely makes it into the headlines. A conversation about what we genuinely do not know, about the questions that sit quietly beneath the surface of every confident announcement, unspoken, not because scientists are hiding anything, but because the answers are so profoundly uncertain that even the most careful phrasing feels inadequate. Today, we are going to have that conversation. We are going to travel to the edge of the observable universe and ask the questions that official statements tend to sidestep. What is actually out there beyond the limit of what we can see? Does the universe have a physical boundary? Or does it simply go on forever? What do our best models actually predict? And how confident, really, are the people who built those models? Because here is the truth that sits beneath the surface of every cosmic map ever drawn. The observable universe, for all its staggering scale, is almost certainly not the entire universe. It is simply the part of the universe from which light has had time to reach us since the beginning of everything. And beyond that bubble of visibility lies something that science can reason about, speculate about, model with breathtaking mathematical sophistication, but cannot, even in principle, directly observe. This is the story of what waits at the edge, and beyond it, the horizon. We never talk about. To understand what NASA doesn't say, we first need to understand what it does say. And what it says correctly is that the observable universe extends approximately 46.5 billion light-years in every direction from Earth. Now, immediately, this number raises a question that any sharp mind will catch. If the universe is only 13.8 billion years old, how can light from 46.5 billion light-years away have possibly reached us? Light travels at a finite speed. Shouldn't the farthest we can see be 13.8 billion light-years? 1 light-year for every year the universe has existed? This discrepancy is not an error. It is one of the most important and most underappreciated facts in all of cosmology. The universe has been expanding since the moment of the Big Bang. Space itself has been stretching, and the regions of space from which the oldest light originated have, since that light departed, been carried away from us by the expansion of space at speeds that, when accumulated over 13.8 billion years, far exceed the speed of light. This is not a violation of relativity. Einstein's speed limit applies to objects moving through space. It does not apply to the expansion of space itself. Space can and does expand faster than light. And this means that the most distant light reaching our telescopes today originated from regions that are now, due to that expansion, roughly 46.5 billion light-years away. That boundary, the edge of what we can observe, is called the particle horizon. It is the cosmological equivalent of the horizon you see standing on a beach. Beyond it, there is certainly more ocean. The horizon is not the edge of the ocean. It is simply the limit of your vision given your height and the curvature of the Earth. The particle horizon is the limit of our cosmic vision, given the finite speed of light and the finite age of the universe. And just as no one would seriously argue that the ocean ends at the visible horizon, no serious cosmologist argues that the universe ends at the particle horizon. But here is what the official briefings tend to gloss over. There is a second horizon, a more troubling one, and unlike the particle horizon, which is merely the limit of our past visibility, this second horizon defines something more fundamental. It defines the limit of our future, the limit of what we can ever know, not just now, but at any point in the future, no matter how powerful our telescopes become. This is the cosmic event horizon, and it is shrinking. Right now, the cosmic event horizon sits at approximately 16 billion light-years from Earth. Any galaxy currently beyond that boundary is receding from us so rapidly, due to the accelerating expansion of the universe, that no signal it sends today, no light, no radio wave, no gravitational wave, will ever reach us. We are already, right now, permanently cut off from communication with the majority of the observable universe's galaxies, let alone whatever lies beyond our observational bubble. And the expansion is accelerating. Dark energy, the mysterious component that makes up roughly 68% of the total energy content of the universe, is pushing everything apart at an increasing rate. As time goes on, the event horizon will contract further. More and more of what we can currently see will cross that boundary and disappear from our future reach forever. In roughly 2 trillion years, if the current cosmological models are correct, essentially everything beyond the local group, the gravitationally bound cluster of galaxies that includes the Milky Way, will have receded beyond our event horizon. Astronomers of that distant era, if any exist, will look out into what appears to be an almost completely empty universe. The cosmic microwave background will have redshifted to wavelengths too long to detect with any plausible instrument. The rich tapestry of galaxies we see today will have vanished beyond an impenetrable veil. They will have no way of knowing that we ever saw any of it. They may have no way of knowing that a Big Bang happened at all. This is what sits beneath the confident measurements and beautifully rendered maps. Not error, not deception, simply the profound recognition that what we can see is a temporary gift, and that the universe is actively in the process of taking it back. What lies beyond the observable bubble? So what actually is out there, beyond the 46.5 billion light-year boundary of our visible universe? The honest answer, the answer you will rarely hear stated quite this plainly in a press release, is that we do not know for certain. We cannot observe it. We cannot send a signal there. We cannot, even in principle, receive any information from the regions of the universe that have always been beyond our particle horizon. And yet, physics is not silent on the question. The most broadly accepted cosmological model, the lambda CDM model, that describes a universe dominated by cold, dark matter and a cosmological constant representing dark energy, makes a straightforward prediction when pushed beyond the observable boundary. It predicts more of the same. More galaxies, more galaxy clusters, more cosmic web filaments connecting them, and voids separating them, statistically similar to what we observe within our bubble. The universe, on the largest scales, is expected to look roughly the same everywhere, a principle called the cosmological principle. And our observable region, however large it seems, is almost certainly too small a sample to have captured any gross deviation from this rule. But here is where it gets genuinely extraordinary. If the universe is truly infinite, and our current models are perfectly consistent with an infinite universe, then the implications are almost impossible to absorb. An infinite universe with a statistically uniform distribution of matter means that every possible configuration of matter must, somewhere, actually exist. Not just similar configurations, identical ones. In an infinite universe, there is somewhere a galaxy identical to the Milky Way. Within it, a solar system identical to ours. Within that, a planet identical to Earth, with identical continents, identical oceans, and identical history. And on that planet, someone identical to you is reading or watching something identical to this. The probability of any specific configuration of matter arising is extremely small but finite. In an infinite universe, finite probability events happen infinitely many times. This is not mysticism. This is combinatorics. The number of possible configurations of matter within a region, the size of our observable universe, is extraordinarily large but finite, bounded by the number of particles that could fit into that volume, and the number of energy states each could occupy. In an infinite universe, every one of these finite configurations repeats, infinitely. The nearest identical copy of our observable universe, given the density of matter we observe and the number of possible quantum states, would lie at a distance so enormous that the number of zeros required to write it would itself fill this script many times over. But the distance, however incomprehensible, is finite. And in an infinite universe, finite distance is not a barrier. It is simply a very, very long wait. Whether the universe is actually infinite is a question that our current observational capabilities cannot resolve. The geometry of the universe, whether it is perfectly flat, very slightly positively curved like the surface of a sphere, or very slightly negatively curved like a saddle, determines whether it is finite or infinite. The cosmic microwave background measurements suggest, with extraordinary precision, that the universe is very close to geometrically flat. Perfectly flat means infinite. A tiny positive curvature means finite but unbounded, like the surface of a very large sphere. The measurements are consistent with flatness to a precision of about 1%. What lies within that 1% of uncertainty is, potentially, the difference between an infinite universe and a merely incomprehensibly large finite one. And here is the uncomfortable truth. That 1% of uncertainty will never fully collapse. The systematic uncertainties in cosmological measurements, the difficulty of modeling all the relevant physics perfectly, the statistical noise inherent in working with a finite observational sample, will always leave open a sliver of geometric ambiguity. The question of whether the universe is truly infinite may be permanently beyond resolution by any observer confined within a finite observational bubble. This is not NASA being evasive. This is physics, operating at the limits of what any observer anywhere in the universe can ever know. The multiverse, speculation, or science. Beyond the question of what lies in the unobservable extensions of our own universe, lies an even more radical possibility. One that cosmologists talk about freely in technical papers and at conferences, but that rarely makes it into the carefully worded public communications of major space agencies. The possibility that our universe is not the only universe. The multiverse is not a single theory. It is a family of possibilities, each arising from different areas of theoretical physics, each with its own character and its own degree of speculative leap beyond what observation can currently confirm. The most conservative version arises directly from the standard cosmological model. If the universe is infinite, and if other regions beyond our observational bubble exist and evolve independently, then, in a meaningful sense, those regions are separate universes, islands of observation separated by distances no signal can ever cross. This Level 1 multiverse, as it has been called, requires nothing exotic at all. It is simply the standard cosmological model pushed to its logical conclusion. The Level 2 multiverse arises from cosmic inflation, the extraordinarily rapid expansion thought to have occurred in the first tiny fraction of a second after the Big Bang. In eternal inflation models, which many cosmologists consider the most natural outcome of inflationary physics, inflation never fully stops. It continues forever in most regions of spacetime, with local pockets of non-inflationary expansion, like bubbles in an eternally boiling sea, producing individual universes. Our universe, on this view, is one such bubble, and other bubbles may exist, each potentially with different physical constants, different masses for elementary particles, even different numbers of spatial dimensions. The implications of bubble universes with different physical constants are staggering. In our universe, the strength of the electromagnetic force, the ratio of the proton to the electron mass, the cosmological constant, all set at values that appear, with suspicious precision, to permit the existence of stars, planets, chemistry, and life. Adjust most of these values even slightly, and the universe becomes sterile. Atoms cannot form. Stars burn out in seconds. The cosmological constant, if slightly larger, would have caused the universe to fly apart before any structure could form at all. For decades, this remarkable fine-tuning was a puzzle, without a satisfying explanation. But if inflation produces vast numbers of bubble universes, each with randomly assigned physical constants drawn from some probability distribution, then the fine-tuning becomes comprehensible. We observe the values we do not because they were specially chosen, but because only a universe with these approximate values could contain observers capable of noticing anything at all. We are here to measure the constants precisely, because the constants permit our existence. This is the anthropic principle. It is not a complete explanation. It doesn't tell us what determines the probability distribution from which the constants are drawn, and it depends on the correctness of eternal inflation, which has not been directly confirmed. But it transforms fine-tuning from a mystery into a selection effect, and it suggests that the most fundamental properties of our universe may be the result of cosmic chance rather than cosmic design. The Level 3 multiverse arises from quantum mechanics. In the many worlds interpretation, first proposed by physicist Hugh Everett in 1957, quantum events do not have unique outcomes. Every time a quantum measurement occurs, every time a particle takes one path instead of another, every time a radioactive atom decays or does not decay in a given moment, the universe splits. Both outcomes happen. They happen in separate branches of a vast quantum superposition. The universe that results is an endlessly branching tree of realities, all equally real, none communicating with the others. In this interpretation, there's a branch of reality in which every event that could have happened did happen. Every decision you ever made has a branch in which you chose differently. Every historical turning point has branches in which it turned another way. Every cosmic accident, every near-miss asteroid, every slightly different stellar evolution has a branch in which it went the other way. The many worlds interpretation is not fringe physics. It is one of the most seriously debated interpretations of quantum mechanics, favored by a significant minority of physicists, precisely because it takes the mathematics of quantum mechanics entirely at face value without adding any additional assumptions about wave-function collapse. But it is also deeply strange, and what it implies about the nature of reality is something that most scientific communication hesitates to spell out. Each of these multiverse scenarios is consistent with known physics to varying degrees. None of them is confirmed by direct observation. All of them make predictions that are, at least in principle, partly testable, though the testing is extraordinarily difficult and in some cases may require conceptual advances in theoretical physics that have not yet been made. This is precisely why you rarely hear them stated as established fact in official communications. They live in the productive twilight between rigorous theory and confirmed observation, and responsible science communication treads carefully in that space. But this caution can, if misread, give the impression that these ideas are less serious than they are. They are not the products of undisciplined imagination. They are the careful extensions of our best tested theories into regimes beyond the reach of current instruments, and they represent humanity's most sophisticated current attempt to answer the oldest question of all. Is there more than this, the shape of everything? Here is something that rarely makes it into the popular discussion of cosmic edges. The question of what lies beyond the observable universe is not just a question of how much matter and space there might be. It is also a question of shape. Our universe has a geometry. Space-time is not merely a passive container for matter and energy. It is a dynamic, flexible structure that curves in response to mass and energy, as Einstein's general theory of relativity describes with extraordinary precision. And on the very largest scales, scales far larger than individual galaxies or even galaxy clusters, space-time has an overall curvature that determines its global geometry. The three possibilities are, in a rough analogy with two-dimensional surfaces, something like a sphere, a flat plane, and a saddle. A spherical universe is positively curved, finite in volume, and has no boundary, just as the surface of a sphere has finite area but no edge. You could travel in any direction in such a universe and eventually return to your starting point. A flat universe extends infinitely in all directions with no curvature. A saddle-shaped universe is negatively curved and also infinite. The cosmic microwave background, that ancient afterglow of the Big Bang's first light, the oldest electromagnetic signal we can detect, carries encoded within it information about the geometry of the universe. The angular sizes of the temperature fluctuations in this background radiation depend sensitively on the universe's curvature, and when these angular sizes are measured with precision, using instruments like the WMAP and Planck satellites, the answer that emerges is a universe extraordinarily close to geometrically flat. Not exactly flat, necessarily, just very close to flat. And because the measurements have a small but irreducible uncertainty, we cannot say with certainty whether the universe is perfectly flat and therefore infinite, or slightly curved and therefore finite, but so enormously large that its curvature is undetectable within our observational bubble. But the concept of the universe's shape runs deeper than mere geometry. There is a field of mathematics called topology that studies the global connectivity of spaces, not just their local curvature, but the way they are connected at large. A flat geometry does not uniquely determine the topology. A flat, infinite plane and a flat, finite torus, the shape you get by connecting opposite edges of a square, producing a geometry like the screen of a video game where going off one edge brings you back on the other, have the same local geometry but radically different global topologies. In a toroidal universe, you could, in principle, look far enough in one direction and see the back of your own head. Not really, because the universe is much larger than our observational bubble, even in finite topologies consistent with current measurements. But the principle holds. Some configurations of finite, flat space allow you to travel in one direction and eventually return to where you started. Cosmologists have searched the cosmic microwave background for signs of such topology, patterns that would indicate we are looking at the same distant region of space from multiple angles. So far, no convincing topological signature has been found, but the absence of detection does not rule out a finite topology. It simply means that if the universe does wrap around on itself, it does so on scales larger than our observational bubble. Larger, in other words, than the 46.5 billion light-year radius of everything we can see. The shape of the universe at the very largest scales may be, in the most literal possible sense, beyond observation. Not just currently beyond observation, pending better instruments. Beyond observation in principle, for any observer constrained by the same light speed limit and the same finite cosmic age that constrains us. And this is something rarely stated in the summary paragraphs of press releases. The overall shape of the universe, whether it is finite or infinite, whether it wraps around on itself, whether it is simply connected or has exotic topological features, may be permanently unknowable. Not because we have failed to look, but because the universe is structured in a way that places the evidence for its global shape forever beyond the reach of any internal observer. He walls at the edge of everything we can see. Within the observable universe itself, within our 46.5 billion light-year bubble, we have discovered that structure exists at scales that push the boundaries of the cosmological principle itself. For decades, cosmologists assumed that while local structure was complex, stars, galaxies, clusters, superclusters, the universe on the very largest scales would be smooth and uniform. This expectation was enshrined in the cosmological principle, the assumption that the universe is, on its grandest scales, both homogeneous, the same density everywhere, and isotropic, looking the same in every direction. The evidence from galaxy surveys seemed consistent with this picture. But as those surveys grew larger and more detailed, something unexpected began to emerge. The universe has structure at scales far larger than the standard cosmological models had predicted. The Great Wall, the Sloan Great Wall, the Hercules Corona Borealis Great Wall. These are not poetic names for modest features. They are descriptions of structures containing billions and billions of galaxies, stretched across hundreds of millions or even billions of light years. Filaments, sheets, and walls of matter so vast that if you were to zoom out to the scale at which the entire observable universe fits on a page, these structures would be visible features, creases and folds in the cosmic fabric. The Hercules Corona Borealis Great Wall, currently the largest known structure in the observable universe, spans an estimated 10 billion light-years. It is so large that it represents a challenge to our theoretical expectations. At that scale, the universe is supposed to have smoothed out. Structure of that magnitude should not, according to the Standard Model, exist. Its existence raises questions. Is the cosmological principle an oversimplification? Does the universe have structure at even larger scales, scales comparable to or exceeding our observational bubble, that we simply cannot see because we are inside it? Are our models missing something about how structure forms on the very largest scales? These are not questions that have comfortable official answers. They are live debates in the scientific literature, generating papers and responses and further analyses. And they suggest that even within the part of the universe we can observe, we may not have a complete picture of the largest patterns. Beyond the walls and filaments, there are the voids, enormous regions of space where galaxy density drops to a tiny fraction of the cosmic average. The Botas void, discovered in 1981, spans roughly 330 million light-years, a region of space in which, where we would normally expect to find thousands of galaxies, only a handful exist. The Eridanus supervoid extends perhaps 1 billion light-years across and has been tentatively linked to the mysterious cold spot in the cosmic microwave background, a patch of the ancient light map that is cooler than its surroundings by an amount that current models struggle to fully explain. These vast structures, the walls and the voids, are the architecture of the universe on the largest scales we can probe, and they are telling us something. They are telling us that the early universe, in the first tiny fractions of a second after the Big Bang, was not perfectly smooth. It had fluctuations, density variations, quantum uncertainties blown up to cosmic scale by the rapid expansion of inflation. And those tiny variations, amplified over 13.8 billion years by gravity and dark energy, and the complex physics of cosmic structure formation, produced the web of walls and voids we observe today. But here's the question that sits quietly at the edge of this picture. If the universe contains structure at scales of 10 billion light-years within our observable bubble, might it contain structure at scales of 100 billion light-years, of 1 trillion light-years, of scales so large that our entire observable universe is simply one small, statistically uniform patch within a much larger pattern of cosmic architecture that we cannot access? We do not know. We cannot know. The light from those scales has not reached us, and never will. The expansion that never stops. One of the most significant discoveries in the history of astronomy came in 1998, when 2 independent teams studying distant supernovae discovered that the expansion of the universe is not slowing down, as gravity would suggest. It is accelerating. The universe is not merely growing, it is growing faster with every passing moment. And the agent responsible for this acceleration, dark energy, comprising approximately 68% of the total energy content of the cosmos, is something we understand almost not at all. We know dark energy exists because of what we observe. The mathematics of general relativity, applied to a universe that is accelerating in its expansion, requires an energy component with a negative pressure, a component that acts at large scales in opposition to gravity. We call it dark energy. We describe it with a cosmological constant in our equations. We measure its effects with extraordinary precision. But what it actually is, what its physical origin might be, remains one of the most profound open questions in all of science. The simplest interpretation is that it is the energy of the vacuum itself, an intrinsic property of empty space, a baseline energy density that pervades every cubic centimeter of the universe, whether matter is present or not. This interpretation is appealing in its simplicity. It is also deeply troubling. When physicists calculate the vacuum energy expected from quantum field theory, from the known properties of quantum fields and their zero-point fluctuations, they get an answer that disagrees with the observed value of the cosmological constant by a factor of approximately 10 to the power of 120. This is not a small discrepancy. It is the largest known discrepancy between theory and observation in the history of physics. Some physicists consider it the most embarrassing number in science. Various proposals have been made to explain the discrepancy. Perhaps the vacuum energy contributions from different quantum fields nearly cancel, with the observed value being a tiny residue of almost perfect cancellation. Perhaps dark energy is not actually a constant, but varies with time, a dynamic field called quintessence that evolves as the universe evolves. Perhaps it is a consequence of modifications to general relativity at very large scales. Perhaps it arises from extra spatial dimensions beyond the three we experience. Each of these proposals has its adherents. None has been confirmed. And the measurements required to distinguish between them, measurements of the cosmic expansion history with sufficient precision to detect any variation in dark energy over time, are the goal of some of the most ambitious observational programs currently underway. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional distribution of galaxies across the observable universe with extraordinary precision, specifically to measure the history of cosmic expansion and the growth of large-scale structure. The Nancy Grace Roman Space Telescope, planned by NASA for launch in the late 2020s, will similarly map vast volumes of cosmic space to constrain the nature of dark energy. But here is what those missions, however successful, will not be able to tell us. They will not tell us why dark energy has the value it does. They will not tell us whether it is truly constant or slowly varying. They will not tell us what it fundamentally is. They will constrain our models with greater precision and help us determine which mathematical description fits the observations best. Understanding rather than description, knowing not just that dark energy has a particular value, but why it has that value, may require theoretical advances that have not yet been made, advances that may need to wait for a complete theory of quantum gravity, which itself remains one of the greatest unsolved problems in physics, and in the meantime, dark energy continues its work, implacably stretching space, inexorably carrying galaxies beyond our event horizon, slowly but certainly dismantling the observable universe as a meaningful scientific resource. The universe is not simply sitting there waiting to be explored. It is actively in the process of becoming less explorable. The window of maximal cosmic visibility, the era in which a civilization equipped with sufficient technology could see the largest possible number of distinct galaxies and conduct the most comprehensive survey of cosmic structure, may well be the era we are living in right now. A few billion years in either direction, and the picture changes dramatically. Earlier, and the universe was too young and hot for much of the current structure to have formed. Later, and the accelerating expansion will have erased much of it from our view. We are, in a very real sense, living at an extraordinary moment in cosmic history, and the questions we manage to answer in this era may be the only chance any civilization in our region of spacetime will ever have to answer them. The flatness problem and the fine-tuned beginning. there is a question buried inside the standard cosmological model that rarely makes it into the public-facing summaries. It is called the flatness problem, and it points to something extraordinary about the conditions of the very early universe. We have established that the universe appears to be geometrically flat, that measurements of the cosmic microwave background place its curvature extraordinarily close to zero. This is, on its surface, a measurement, a result, a conclusion supported by data. But when you follow the mathematics of cosmic expansion backward in time, asking what curvature the universe must have had at earlier moments to produce the near-perfect flatness we observe today, something remarkable emerges. The universe's expansion is structured so that any initial curvature, if it exists, becomes amplified as time goes on. A universe that starts with a slight positive curvature will become more curved as it ages. A universe with a slight negative curvature will become more negatively curved. What this means is that a universe as flat as ours is now must have been extraordinarily flat at earlier times. To produce the flatness we observe today, the universe at 1 second after. The Big Bang must have had a curvature parameter matching the critical flat value to within about 15 decimal places. At the Planck time, the earliest moment that our physics can meaningfully address, the required flatness was even more extreme. The initial conditions of the universe were, by any standard measure, astonishingly, improbably, precisely calibrated. This is the flatness problem. It is not a problem in the sense of a contradiction or an error. It is a problem in the sense that it demands an explanation. Why was the universe so extraordinarily flat at its beginning? What physical mechanism produced initial conditions of such precise calibration? The standard answer, the one offered by cosmic inflation, is elegant and powerful. During the inflationary epoch, the period of exponentially rapid expansion in the universe's first moments, any initial curvature would have been stretched away to essentially zero, just as the curvature of a balloon's surface becomes less and less apparent as the balloon is inflated. Inflation naturally drives the universe toward flatness, regardless of initial conditions, as long as inflation lasts long enough. This is one of inflation's great successes. It explains not just flatness, but also the remarkable uniformity of the cosmic microwave background. The fact that regions of the universe that, without inflation, could never have been in causal contact have essentially identical temperatures. Inflation stretched a tiny, causally connected region to encompass the entire observable universe, smoothing out any initial temperature differences in the process. But inflation's success brings its own question. What drove inflation? What is the inflationary field, the so-called inflaton, and what are its physical properties? How did inflation begin? And what determined when it ended? These questions remain open. The general framework of inflation is broadly accepted by cosmologists, but the specific model of inflation that applies to our universe, there are hundreds of viable candidates in the theoretical literature, has not been determined. The detection of primordial gravitational waves in the polarization pattern of the cosmic microwave background would provide crucial discriminating information. Different inflationary models predict different amplitudes for these primordial gravitational waves, parameterized by a quantity called the tensor-to-scalar ratio. Measuring this quantity, or placing a sufficiently stringent upper limit on it, could rule out large classes of inflationary models and sharpen our understanding of the first moments of cosmic history. This measurement is the primary scientific goal of the next generation of cosmic microwave background experiments, including those being planned at the South Pole and in space. it is extraordinarily difficult. The primordial gravitational wave signal, if it exists at detectable levels, is buried beneath the foreground emission of dust in our own galaxy, and the secondary polarization signals generated along the long path the microwave background photons have traveled. Separating the primordial signal from these contaminants requires observations across many different wavelengths and exquisitely careful data analysis. And here is what is quietly understood in the field. Even a successful detection of primordial gravitational waves would not fully confirm inflation. It would confirm that something produced tensor perturbations at the right amplitude in the early universe. Inflation is the leading theoretical explanation for such perturbations, but alternatives have been proposed. Models involving a bouncing universe, string gas cosmology, matter bounce scenarios that also predict primordial tensor perturbations with somewhat different spectral properties. The full confirmation of inflation, if it can ever be achieved, will require not just a detection, but a precise measurement of the tensor spectrum, the scalar spectral index and its running, and the non-Gaussianity of the primordial fluctuations. Each of these measurements requires pushing current technology further, and each measurement will add information to the picture without providing a complete and unambiguous answer. This is not a criticism of the science. It is a description of how science at the frontier actually works. Piece by piece, measurement by measurement, the picture sharpens, the uncertainty narrows, the space of viable models contracts, and eventually, perhaps, a single model survives. What that model will look like, what it will imply about the first moments of cosmic existence, and about the conditions that preceded them, we cannot know in advance. The universe has surprised us at every previous juncture. There is no particular reason to assume the next surprise will be smaller than those that came before. The signals. We cannot send and cannot receive communication requires two things, a sender and a receiver. And it requires that whatever signal passes between them travels at a speed sufficient to cover the distance in a time less than the relevant deadline. The relevant deadline, in cosmic terms, is the event horizon. Cross it, and the signal never arrives. We have, as a civilization, been broadcasting electromagnetic signals into space for roughly a century. Radio waves, television transmissions, radar pulses, deliberate signals aimed at specific targets, the incidental electromagnetic leakage of an industrialized civilization. All of it expanding outward from Earth at the speed of light in an ever-growing sphere. That sphere currently has a radius of perhaps 100 light years. It encompasses a modest number of stellar systems, none of which we have any evidence of hosting technological civilizations. But think about what this means for communication with the wider universe. The event horizon sits at 16 billion light years. Any signal we send today toward a galaxy currently sitting just outside that boundary will never arrive. The galaxy is receding too quickly. Space between us and it will grow faster than light can cross it. Our signal, no matter how powerful, will travel toward its destination forever without getting there, perpetually outpaced by the very fabric of space it is trying to cross. Conversely, any civilization currently situated at a distance greater than 16 billion light years from us has already lost the ability to affect our future in any way. Their light, their gravitational waves, their hypothetical signals, none of it can reach us. We are already causally disconnected. We will never learn of their existence, however advanced they might be, however loud their transmissions. For the galaxies and stars and potential civilizations currently between the particle horizon and the event horizon, those between 16 and 46.5 billion light-years away, the situation is more nuanced. Their ancient light is visible to us now, but any signal they sent more recently, after the expansion of space put them outside our event horizon, is likewise lost. We see their past. We can never know their present or future. There is something profound in this picture. The universe contains, almost certainly, an enormous number of other regions of matter and energy, and potentially even consciousness. Some of those regions are accessible to us in principle, close enough that signals sent now might eventually arrive, given sufficient time. Others are forever beyond reach, not because of distance in the conventional sense, but because the expansion of space creates an insurmountable barrier that no physical agency can overcome. The universe is not just large. It is structured in a way that guarantees permanent isolation between most of its parts. This has implications that go beyond the merely logistical. The question of whether we are alone in the universe, one of the deepest and most compelling questions human beings have ever posed, may be, in a very specific sense, permanently unanswerable, even if the answer is no. There may be an abundance of other civilizations in the unobservable universe, in the bubble universes of an inflationary multiverse, in the other branches of a quantum mechanical many-worlds reality. But if they lie beyond our event horizon, their existence can neither be confirmed nor communicated. The search for extraterrestrial intelligence, SETI, operates within these constraints. It looks for signals originating within the observable universe, from civilizations close enough that their transmissions can still reach us. It has not yet found any confirmed signal, but the search has barely begun, in any meaningful sense, and the parameter space of possible frequencies, directions, encoding schemes, and signal types is so vast that even a century of searching has covered only a tiny fraction of it. What we can say with confidence is this: any answer we find will come from our cosmic neighborhood. The wider universe, for all its almost certain richness, is beyond the reach of any conversation we might ever initiate or receive. Dark matter, the invisible architecture of everything. Before we reach the signals we cannot send and cannot receive, we must acknowledge another of the great silences in our cosmic map, another vast component of the universe that we know exists, that we have measured with precision, and that we do not understand at the most fundamental level. Dark matter, the invisible scaffolding upon which all visible structure is built. The evidence for dark matter is overwhelming and comes from many independent directions. The rotation curves of spiral galaxies, the way stars and gas in the outer regions of galaxies orbit their galactic centers faster than the visible mass of those galaxies could possibly explain. The gravitational lensing of distant galaxies by intervening galaxy clusters. The bending of light by amounts that require far more mass than the visible matter in those clusters provides. The formation of large-scale cosmic structure, the mathematical models that successfully reproduce the observed distribution of galaxies, require a component of matter that interacts gravitationally, but does not emit, absorb, or reflect electromagnetic radiation. We know dark matter is there. We know it makes up approximately 27% of the total energy content of the universe, more than 5 times the contribution of all visible, ordinary matter combined. We know it forms halos around galaxies, providing the gravitational wells within which galaxies form and evolve. We know its spatial distribution through gravitational lensing maps, that have traced its architecture across large fractions of the observable universe. What we do not know, and what years of increasingly sophisticated searches have so far failed to reveal, is what dark matter actually is. The leading candidates include weakly interacting massive particles, WIMPs, which are predicted by certain extensions of the standard model of particle physics, particularly supersymmetry. Decades of underground detectors searching for the rare recoil of atomic nuclei struck by passing dark matter particles have not found a confirmed signal. Searches at particle colliders, including the Large Hadron Collider at CERN, have likewise not produced the new particles that supersymmetry requires. The parameter space of WIMP dark matter has been significantly constrained, though not eliminated. Other candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics, primordial black holes of various mass ranges, and entirely new sectors of physics that interact with ordinary matter only through gravity. Each candidate has dedicated search programs underway. None has been confirmed. This prolonged absence of a direct detection is, for the field, a challenge to the conventional picture. If dark matter consists of particles with properties similar to what the most natural theoretical models predicted, we should have found them by now. The fact that we have not suggests that dark matter particles interact with ordinary matter even more weakly than initially expected, or that dark matter has a character quite different from what theory suggested, or that new physics beyond the standard model takes a form we have not yet imagined. Some researchers have proposed that dark matter does not exist at all, that the observations attributed to it can instead be explained by modifications to the laws of gravity at low accelerations, a class of theories known as modified Newtonian dynamics, or MOND, and its relativistic extensions. These theories successfully reproduce the rotation curves of many individual galaxies without invoking dark matter. But they struggle to explain the large-scale structure of the universe, the cosmic microwave background fluctuations, and the behavior of colliding galaxy clusters like the Bullet cluster, where the dark matter component and the ordinary matter component have been separated by the collision in ways that gravity modification theories find difficult to account for. The Bullet cluster observation, in particular, is often cited as among the most compelling direct evidence for dark matter. In this system, two galaxy clusters have passed through each other. The ordinary matter, the hot gas that constitutes most of the visible mass in galaxy clusters, was slowed by electromagnetic interactions during the collision and lags behind the galaxies themselves. But the gravitational mass of the clusters, as mapped by gravitational lensing, tracks the galaxies rather than the gas. The mass is where the gas is not. This is exactly what dark matter halos, which interact only gravitationally and pass through each other without slowing down, would produce. Whatever dark matter is, it is not nothing, and whatever it turns out to be, whatever new physics is required to explain it, that physics will likely transform our understanding of the universe in ways we cannot currently predict. The history of dark matter is, in miniature, the history of cosmology itself. Unexpected observations, a long search for explanation, an accumulating realization that the universe contains components whose nature we had not imagined, and a slow, painstaking effort to characterize those components well enough to understand them. We are, with dark matter, somewhere in the middle of that process. The characterization is detailed. The understanding remains elusive. But the search continues, with growing sophistication and with the recognition that the answer, when it comes, will open doors that we cannot yet see, the first light and what it cannot tell us. The cosmic microwave background is, in a very real sense, a wall. We can see it. Our instruments can measure its temperature to extraordinary precision, a uniform 2.725 degrees above absolute zero, with tiny fluctuations of roughly 1 part in 100,000 that encode the seeds of all cosmic structure. We have mapped it in exquisite detail. We have extracted from it measurements of the universe's age, its composition, its geometry, and the amplitude and spectrum of the primordial fluctuations that shaped everything. But we cannot see through it, and this is not a limitation of current technology. It is a fundamental physical barrier, as absolute as the event horizon of a black hole. The cosmic microwave background formed approximately 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was filled with an opaque plasma of charged particles. Light could not travel freely. It scattered almost immediately off electrons, as light scatters in a dense fog. The universe was opaque. When neutral atoms formed, the fog lifted. The universe became transparent. The photons that had been trapped in the plasma were suddenly free to travel, and they have been traveling ever since, cooling and redshifting as the universe expanded around them, arriving at our detectors today as the microwave background we measure. But everything that happened before 380,000 years, the Big Bang itself, the period of inflation, the formation of the first quarks and protons and light nuclei, is hidden behind this electromagnetic curtain. No photon from that era can reach us. The electromagnetic spectrum, however carefully studied, however powerfully instrumented, cannot tell us directly what happened before the universe was 380,000 years old. Neutrinos are an exception. These nearly massless, nearly non-interacting particles decoupled from the rest of matter even earlier than photons did, about 1 second after the Big Bang. A cosmic neutrino background, analogous to the microwave background but originating from this earlier moment, should exist and pervade the universe today. We have indirect evidence for its existence. The standard model of cosmology predicts its contribution to the total energy density of the early universe, and measurements of the microwave background and of the abundances of light elements formed in the Big Bang are consistent with this prediction. But directly detecting these relic neutrinos, whose energies have been redshifted to extraordinarily low values by 13.8 billion years of cosmic expansion, is beyond the reach of any current or near-future detector. Gravitational waves offer the deepest potential window. Unlike electromagnetic radiation or neutrinos, gravitational waves from the very early universe, potentially from inflation itself, or from phase transitions in the first fractions of a second, would have passed through the plasma era without scattering. They would be propagating through space today, redshifted and weakened by cosmic expansion, but theoretically carrying direct information about conditions before the microwave background was formed. Detecting them requires instruments of extraordinary sensitivity. Space-based gravitational wave observatories, planned for deployment in coming decades, may eventually be sensitive enough to detect a stochastic background of gravitational waves from the early universe. If such a background is detected, and its spectrum matches the predictions of specific inflationary models, It would constitute the most direct probe of cosmic history we have ever achieved, a direct glimpse behind the wall. But even gravitational waves have their limits. Quantum gravity effects, which would have been dominant in the first tiny fractions of a second after the Big Bang, in the Planck epoch, when the temperature was so extreme that the distinction between space and matter breaks down entirely, cannot be probed even by gravitational waves. The Planck epoch is not just observationally inaccessible, it is theoretically inaccessible, because our best theory of gravity, general relativity, ceases to function in that regime, and we do not yet have a replacement. What happened in the first 10 to the power of -43 seconds of the universe's existence? The Planck time is genuinely unknown, not poorly constrained, not approximately understood, unknown. The physics of that instant may be the most important physics in existence, the foundation on which everything else rests, and it lies behind a barrier of theoretical opacity that may not yield without a revolution in fundamental physics of a magnitude that has not occurred in a century. What it means to live at the boundary. There is an old thought experiment in physics. Imagine a being of perfect knowledge, a being that knows the position and velocity of every particle in the universe at a given moment, and that possesses unlimited computational power. Such a being, the argument goes, could predict the entire future of the universe and reconstruct its entire past. Every event, every thought, every coincidence would be, for this being, simply the inevitable working out of initial conditions. This thought experiment was proposed as a demonstration of strict determinism, but modern physics has dismantled it in layers. Quantum mechanics showed that even perfect knowledge of initial conditions cannot, in principle, predict individual quantum outcomes. Only probabilities can be known. The hidden variable theorems of Bell and others showed that this indeterminacy is fundamental, not merely a reflection of our ignorance. And cosmology has added another layer. Even if determinism somehow applied, even if the universe were entirely classical and predictable, the cosmological horizons we have been discussing ensure that no observer within the universe can ever possess the complete initial conditions. The universe is structured so that no internal observer can ever have a view of the whole. The event horizon is not just a practical limitation. It is, in a very deep sense, built into the architecture of a universe with dark energy and accelerating expansion. We are local beings, embedded in a cosmos that is fundamentally inaccessible at its full extent to any observer anywhere within it. Every civilization in every galaxy is working from a partial dataset. Every cosmological map ever drawn is a map of one region, with vast and permanent blank spaces at the edges. This might seem humbling, and it is, but it is also, in a different light, remarkable. The fact that we have gotten as far as we have, that creatures evolved on a small, rocky planet, orbiting a modest star in an unremarkable region of a spiral galaxy, have managed, in the span of a few thousand years of accumulated inquiry, to determine the age and composition and geometry of the entire observable universe, is one of the most extraordinary facts about the place we find ourselves in. We have looked back in time to within 380,000 years of the beginning of everything. We have measured the curvature of space-time around objects 1 billion light-years away. We have traced the history of cosmic expansion across most of the age of the universe. We have detected particles that traveled to us through 10 billion light-years of intergalactic space, and arrived with the energy of a tennis ball. We have heard the gravitational echo of two black holes merging when the universe was roughly half its current age. And we have arrived at the edge, not defeated, but informed, knowing precisely what we do not know, knowing the shape of our ignorance with a precision that previous generations could not have imagined. The universe does not owe us answers. It is not arranged for our convenience or calibrated to our instruments. Its most fundamental secrets may be hidden behind barriers, cosmological event horizons, the opacity of the early plasma, the breakdown of physics at the Planck scale, that no future technology can fully overcome. But this has never stopped us before. The history of cosmology is, in large part, the history of finding ways to hear what seemed permanently silent, to see what seemed permanently dark, to measure what seemed permanently beyond reach. Every generation has inherited the open questions of the one before it, and every generation has managed to answer some of them, not all of them, never all of them, but enough to push the frontier another step outward. The questions sitting at the edge of the observable universe today, the nature of dark energy, the global topology of space-time, the physics of the inflationary era, the possibility of other universes, are the hardest questions ever posed in the history of science. They may not all be answerable. Some of them may not be answerable in principle, but they are being asked right now with the most powerful instruments and the most sophisticated theoretical tools ever assembled. And sometimes, not always, not predictably, but sometimes, the universe rewards persistence. Sometimes the signal emerges from the noise. Sometimes the pattern becomes visible. Sometimes the answer turns out to be stranger and more beautiful than anything the question suggested. The edge of the universe is not a dead end. It is an invitation to keep building, keep asking, keep reaching past the boundary of what current instruments and current theories can access. An invitation to accept that the map is incomplete, and that this incompleteness is not a deficiency to be embarrassed about, but the most honest and most productive statement science can make. We do not know what lies beyond the edge. We know that something does. We know that our models suggest it is vast, possibly infinite, possibly populated with structures and patterns, and perhaps even forms of complexity we cannot currently conceive. We know that some of those models have implications so radical that responsible scientific communication hesitates to present them as established fact. And we know that every answer we have ever found to every question we have ever asked has revealed a universe larger and stranger and more generous in its mysteries than the one we thought we understood. The edge is out there. We are moving toward it. And whatever we find when we arrive, one thing is certain. It will not be the end. The questions that official science leaves in the dark. There is no conspiracy here, no suppression, no hidden agenda behind the carefully worded mission statements and the beautifully animated press conference graphics. What there is, instead, is the natural caution of institutions communicating with a broad public about extraordinarily complex and deeply uncertain subjects. Nuance is difficult to communicate in a headline. Uncertainty is difficult to express without sounding confused. And the questions at the very edge of cosmological knowledge, genuinely unresolved questions that the best minds in the world are actively working on, resist the kind of clear, confident summary that translates well into public communication. But this caution, however understandable, can leave the impression that our picture of the universe is more complete than it is. That the beautiful, animated visualizations of cosmic structure represent the whole story. That the measurements, however precise, have given us answers rather than merely more precise versions of old questions. The truth is that the edge of the universe is not a place on a map. It is an epistemological boundary, a line beyond which our ability to gather information runs out. And on this side of that line, the questions accumulate. Is the universe finite or infinite? We do not know. Does the universe have a topology, a global connectivity, that differs from the simplest possibility? We do not know. Does inflation actually occur? And if so, does it produce other bubble universes with different physical laws? We do not know. What is dark energy at a fundamental level? We do not know. What happened in the Planck epoch, in the first instance of the Big Bang? We do not know. Was there something before the Big Bang? And if so, what? We do not know. These are not niche questions. They are not the private obsessions of theorists in isolated offices. They are the central questions of cosmology, the ones that motivate the largest experiments and the most ambitious theoretical programs. And they are unanswered. This is not a failure. It is, on the contrary, an extraordinary achievement. We have gotten close enough to the edge to know exactly how far we are from understanding it. We have mapped the boundary between what we know and what we cannot currently know with sufficient precision to articulate exactly what the open questions are. A century ago, we did not know the universe was expanding. We did not know it had a beginning. We did not know that galaxies beyond the Milky Way existed. We did not know about dark matter or dark energy. We did not know the universe was 13.8 billion years old. We were, epistemologically speaking, nowhere near the real edge of the cosmos. We were confined within the Milky Way in our understanding, as surely as we were confined within the solar system in our travel. In 100 years, we have expanded our observational reach to the edge of the observable universe. We have mapped the cosmic microwave background. We have detected gravitational waves from colliding black holes a billion light-years away. We have photographed the shadows of event horizons. We have traced the history of cosmic expansion back nearly to the beginning of time. And we have discovered, in the process, that the universe is far stranger, far larger, far more mysterious than any previous generation could have imagined. That the observable universe, for all its staggering scale, is almost certainly a tiny and perhaps statistically unremarkable bubble within something far vaster. That the laws of physics, as we know them, may apply only within our particular bubble. That the questions we cannot answer may, some of them, be permanently beyond reach. This is not cause for despair. It is cause for wonder. The universe has proven to be more generous in its mysteries than any prior assessment suggested. Every time we have pushed a boundary, it has receded to reveal something more extraordinary than what we were reaching for. The edge of the universe is not a wall we will one day smash through with a more powerful telescope. It is a horizon, and like all horizons, it moves as we move. As our instruments improve, as our theories deepen, as our understanding of quantum gravity matures and our gravitational wave observatories grow more sensitive, the horizon will shift. Some of what is now beyond reach will come into view, and at the new edge, new questions will be waiting.